Hello, welcome to this video for the Advanced Higher Physics unit of electromagnetism, and this video is on capacitors and in particular reactants. So here are our learning intentions for the video. So we're trying to understand what capacitive reactance is and to be able to calculate it for alternating current and direct current circuits. So we're already familiar with capacitors, and that if we put them in a direct current circuit, the capacitor will charge up, and once the capacitor is fully charged, there will be no more current flowing around the circuit. If we place a capacitor in an alternating current circuit, then the capacitor charges, but then since the current changes direction quite frequently, if it was mains frequency, 50 times per second, then it then discharges. And so in this case, this allows a current to continually flow unless the capacitor can become fully charged in the short amount of time before the current alternates direction. So we've got a graph of current, capacitor charging and discharging at the bottom here for a direct current circuit, and if we have a greater frequency, then the capacitor doesn't become fully charged, so the current doesn't get down to zero, or may not get down to zero. So at high frequencies, the charge is moving more of the time. Capacitors can oppose the flow of an alternating current, as do another component that we learn about in this topic, inductors. The opposition to the flow of an alternating current is called the capacitive reactance and has the symbol X with a C for the capacitance, and is defined by the voltage divided by the current. So the unit is the ohm in the same way as resistance, but it's not the same even though both are on opposition to the flow of current. So let's explore this in a little more detail. So if we want to measure the reactance, we can have a circuit like this one with an alternating current supply and an ammeter and a voltmeter, with the voltmeter connected across the capacitor and the ammeter measure the current through the resistor. And we could measure a pair of particular values at a particular voltage and then do a calculation dividing the RMS voltage by the RMS current. Okay, as we mentioned before, reactance is not quite the same as resistance because resistance causes electrical energy to change into heat, and this doesn't occur in a capacitor. So let's say we've taken two readings and we've got a current reading and a voltage reading. We can work out the capacitive reactance of our capacitor that we're looking at by dividing the RMS voltage by the RMS current. In this case, 18 ohms. Okay, a much better way of doing this is to work out the reactance across a range of different voltages. So if we take a variable voltage supply and we vary the voltage of the power supply, and we record values of the current and the voltage, and we can repeat our readings, so we can reduce our random uncertainty, we can improve our reliability. What we need to make sure of is we need to make sure that variables are kept the same, which in this experiment is particularly looking at the frequency of the alternating current supply. And we can plot a graph of current against voltage, or voltage against current, and we can work out the gradient of the best fit line, which would be the capacitive reactance. A second experiment could be undertaken to look at the effect of the frequency against the current that is measured. And when this is done, where we keep the same voltage but we change the frequency, we can find a relationship that the current is proportional to the frequency. So if we increase the frequency of the alternating current supply, the current increases also through the capacitor. What we have to do in this case is we have to make sure that the voltage stays the same, because if the voltage was changing, then the current would change because of that as well. If we're looking at the reactance, then because the reactance is equal to the voltage divided by the current, and when we have a high current, we have a small reactance, then this means that the reactance is inversely proportional to the frequency. And we can show that the capacitive reactance is equal to 1 over 2 pi times the frequency times the capacitance. Let's just look at this relationship a little more, just to prove that the unit for this is also the ohm. Previously it was straightforward that we were dividing voltage by current, and therefore we would have a unit of ohms. So if we look at frequency first, since frequency is 1 over the period and capacitance is charge over voltage, the unit for frequency times capacitance can be found by multiplying these two terms together. So we've got 1 over time times charge over voltage. So if we multiply those together, we get Q divided by TV. If we divide Q by T, that's the same as current. And so therefore we get current divided by voltage. Okay, and the unit for that would be ohms to the minus 1. And in our relationship at the top, it's 1 over 2 pi FC, and therefore the unit for XC would be the ohm. Okay, you don't need to be able to show this, but it is just showing that the units can be derived from any particular relationship that you have. So if we look at a graph of capacitive reactance against frequency, then we get this inverse relationship curve there. So, and in physics, we always want to plot a graph with a straight line, and therefore we can plot a graph of capacitive reactance against 1 over frequency, and we'll get a straight line graph. And what is more, we can get information from our straight line graph, and the gradient of this particular graph here is going to be 1 over 2 pi times the capacitance. So by plotting these variables, putting a line of best fit, working out the gradient, we can work out the capacitance from our relationship and from our graph. Okay, so the effective rate of flow of charge onto and off a capacitor depends on the capacitance of the reactor and the frequency of the supply. The greater the capacitance, the higher the frequency, the easier it is for charge to continually flow around the circuit. A capacitor's opposition to the flow of an alternating current is called its capacitive reactance XC. And we have our relationships, the one with the frequency and the capacitance in it, and the one with the RMS and the voltage and currents. Okay, so reactance is similar to resistance in DC circuits, but it's frequency dependent. Both resistance and reactance are measured in ohms. So a couple of examples now. If we're given information about a capacitor and the frequency of supply and the RMS voltage, then we can work out the RMS current. So we need to do two steps here. So first step is we need to work out the reactance in ohms, and then having the reactance in ohms and the voltage in volts, we can work out the current. Okay, second example here. Calculate the capacitive reactance of the capacitor in this circuit here. So we're given 10 volts RMS voltage, 60 Hertz, 100 microfarads. So, and then we're going to be asked to work out the current and state what happens when we increase the frequency. So if we double the frequency, what happens to the reactance and what happens to the current. So let's look at the first ones of those there. So since we have the frequency and we have the capacitance, we can work out the reactance using the relationship 1 over 2 pi fc, substituting our answers, and we get 26.5 ohms or 27 ohms. We were then asked to work out the current, and now because we have the reactance and the RMS voltage, we can work out the current straightforwardly. Okay, and finally we're asked what would happen if the frequency of the supply is increased to 120 Hertz. Okay, and this just says state what happens. So if we look at our relationships, well, if we're doubling the frequency, well, we're going to divide by a greater number. In fact, it's going to be divided by twice the number, so the reactance is going to decrease. It's going to be half of what it was previously. If the reactance is half of what it was previously, then the current is going to increase. In fact, it's going to be double what we calculated earlier. So the things you have to know for this particular section is to be able to know and state that capacitive reactance is the opposition of a capacitor to changing current, and to be able to solve problems using the two relationships for capacitive reactance.